Ancient builders did not lack machines. They lacked engines. A lever is a machine. A ramp is a machine. A rope wrapped around a post is a machine. So is a wooden sledge, a plumb line, a water level, a hammerstone, and a group of people pulling at the same moment because someone shouted at exactly the right time. The machines were simple. The results were not. Long before steel cranes, hydraulic cutters, laser levels, electric drills, and trucks capable of moving a house before lunch, humans raised roofs, built villages, cut hard stone, moved blocks heavier than elephants, and aligned monuments closely enough that modern visitors assume something must be missing from the story. Something is missing. It is not an ancient super tool. It is the thousands of ordinary decisions that disappeared when the ropes rotted, the wooden frames decayed, the ramps were dismantled, and the workers went home. Stone survives. The method often does not. And the most important construction tool of all left almost no archaeological trace because it did not have a cutting edge. Let's go through it properly. Start with the phrase modern tools. It quietly suggests that ancient people were trying to perform modern construction with an empty toolbox. They were not. They built structures designed around the materials, labor, climate, and tools available to them. A modern engineer can order a steel beam with standardized dimensions and have it delivered by truck. A prehistoric builder begins by asking a different set of questions. Which trees grow straight? Which stone splits along a useful line? What soil becomes hard when mixed with water and fiber? Where does the wind come from in winter? How heavy can 10 people drag? How heavy can 40? The building begins before anyone touches the site. It begins with knowing the landscape well enough to see construction materials where an untrained person sees trees, mud, grass, and inconvenient rocks. This is why the first human buildings are difficult to reconstruct. Most were made from materials that disappear. Wood rots, plant fiber breaks down, hide decays, thatch burns, mud walls dissolve back into soil. Archaeologists are often left with post holes, hearths, compacted floors, fragments of burned clay, stains in the ground, and impressions left by branches that vanished thousands of years ago. A modern visitor sees an empty field. An archaeologist sees where the walls used to stand. Early shelters did not require monumental technology. A group could bend flexible poles into an arch, tie them together with plant fiber or strips of hide, then cover the frame with grass, bark, reeds, leaves, or skins. The structure worked because each part handled a different problem. The frame carried the load. The covering shed water and blocked wind. The shape redirected force into the ground. No single piece had to be especially strong if the entire structure shared the stress. That principle never went away. Modern buildings still survive by directing forces through a system. Ancient builders simply used systems made from materials they could cut, bend, carry, and replace by hand. The roof was often the hardest part. Walls can stand vertically with enough mass. A roof must remain above the people who built it, resist wind, carry its own weight, and avoid collecting enough rain or snow to become briefly interested in the floor. Steep roofs shed water. Low roofs require less material. Central posts reduce the distance beams must span. Thatch works because thousands of small stems overlap, forcing water to travel outward and down rather than directly through. One reed is not waterproof architecture. 10,000 arranged correctly can be. That word matters. Arranged. Ancient construction was rarely about finding one impossible object. It was about combining ordinary objects so that weakness in one direction became strength in another. Wattle and daub is a perfect example. Builders set upright posts, weave flexible branches between them, then cover the woven wall with a mixture of clay-rich earth, water, and often plant fiber or other temper. The woven branches hold the wet material in place. The daub blocks wind and creates a solid surface. Fiber helps control cracking as the wall dries. The result is not glamorous. It is also a wall. With maintenance, a very useful one. Mud brick extends the brick, same logic. Wet earth is shaped into units, often mixed with straw or other material, then dried in the sun. A loose pile of soil cannot become a tall wall. Thousands of regular blocks can, because regularity allows loads to pass downward predictably. Brickmaking also moves construction away from the exact shape nature provided. A tree remains partly shaped like a tree. A stone remains partly shaped like geology. A brick can be repeated. Once builders can make standard units, they can count them, stack them, estimate labor, divide work, and repair one section without rebuilding everything. The first major construction revolution was not a giant monument. It was repetition. Stone created a different problem. Stone lasts, carries enormous compressive loads, resists fire, and can turn a building into something several generations are forced to notice. It is also heavy, irregular, abrasive, and largely unwilling to cooperate. The first step was choosing the right stone. Ancient builders were not equally impressed by every rock. Limestone can be comparatively easy to quarry and shape. Sandstone may split along bedding planes. Flint fractures into extremely sharp edges. Granite is hard and durable, but punishes weak tools. Some volcanic stones can be rough, but light. Slate separates into thin sheets useful for roofing. The geology determined the toolbox. Then the toolbox revealed more geology. Builders learned where a stone naturally cracked, how grain direction affected splitting, and whether a line of small impacts would create a controlled fracture or an expensive pile of disappointment. Quarrying did not always mean cutting a perfect block out of solid rock from every side. Workers exploited natural joints, bedding planes, weathered surfaces, and existing fractures. They removed material around a desired mass, widened cracks, drove in wedges, struck with stone pounders, and separated the block along the easiest available line. The quarry was part workshop, part negotiation. The stone usually won the first few rounds. For softer stone, chisels and picks could remove material directly. Harder stone was often attacked with harder stone. Ancient Egyptian workers, for example, used percussion and abrasion together. Heavy stone pounders could batter and rough shape hard rock. Copper or bronze tools were useful on softer stones, but hard materials such as granite required more than a soft metal edge. This is where sand becomes a cutting tool. A copper saw touching granite is not impressive. Copper is softer than granite, but the saw can carry loose, abrasive particles across the surface. Quartz-rich sand, water, and repeated movement allow the abrasive grains to scratch and remove tiny amounts of stone. The copper guides the action. The sand does the cutting. This process is slow if measured against an electric saw. It is fast if the alternative is asking the granite politely. Ancient craftspeople used related abrasive methods with saws, drills, rubbing stones, grinders, and polishing materials. A tube drill combined with abrasive slurry could cut a circular groove. A rubbing stone could flatten high points. Repeated grinding could create smooth surfaces that look almost impossible until you remember that slow, multiplied by thousands of hours, becomes a manufacturing method. Time was not free, but it was available in a different form. A modern power tool concentrates energy into minutes. Ancient building concentrated labor into days, seasons, and generations. That did not make the work easy. It changed where the energy came from. Food powered muscles, wooden handles directed force, stone edges concentrated it, rhythm preserved it. A skilled worker does not strike as hard as possible every time. They strike at the angle that removes useful material without destroying the tool, the workpiece, or the hand holding one of them. The difference between a beginner and a craftsperson is often not strength. It is how little effort gets wasted. This is why experimental archaeology matters. When modern researchers try ancient methods, the first attempt often performs terribly. The tool slips, the rope stretches, the stone barely moves. Then technique improves. The same equipment begins doing more. Ancient people did not approach construction as modern office workers attending a team-building activity. Many had learned material skills from childhood. They understood the sound of a good strike, the feel of fiber before it failed, and the point where wet clay had enough water but not too much. Their hands contained measurements no ruler displayed. By the way, if you want to go even deeper into the secret lives of ancient humans, I just launched a full course called The Secret Lives of Ancient Humans. 10 modules, 3+ hours of content covering everything we never talk about on YouTube. What they feared, how they communicated, what hunted them, and much more. Plus an exclusive PDF guide included. Link in the description. See you inside. They also used actual measuring tools. A stretched cord creates a straight line. A weighted cord creates vertical. Water finds level. A shadow records direction and time. A simple square or a carefully formed triangle can establish an angle. Repeated measurements can divide a circle, align walls, and correct errors before those errors become several tons tall. None of this requires a laser. It requires reference points that behave consistently. Gravity does not become more accurate after electricity. Water does not need calibration software to settle horizontally. The challenge is preserving the reference while people work around it. Cords stretch, stakes move, ground settles, sightlines become blocked. A measurement taken correctly once can still be copied incorrectly 20 times. Large construction therefore required checking. Measure. Build. Check again. Correct early. The ruins we admire are usually the projects that survived both engineering and selection. The badly built walls collapsed, were rebuilt, reused, or became low mounds nobody photographs at sunrise. Ancient builders made mistakes. Egypt's bent pyramid changes angle partway upward, probably because the original form created stability concerns. That is not evidence of incompetence. It is evidence of builders responding to a structure while it was still becoming one. Engineering did not arrive as a complete revelation. It learned under load. Moving material created the next problem. Cutting a block is difficult. Convincing the block to leave the quarry is personal. People often imagine ancient stone transport as a competition between muscle and mass. The builders simply gathered an enormous crowd, pulled harder, and hoped the rope had strong spiritual beliefs. Muscle mattered. Friction mattered more. A heavy stone resting directly on rough ground catches, digs in, and resists movement. Put it on a wooden sledge, and the load becomes easier to distribute. Prepare a path, and resistance drops further. Lubricate or firm the surface, and the same pulling force moves more weight. Ancient Egyptian images show huge objects transported on sledges, while liquid is poured onto the ground ahead. Modern experiments with sand found that the correct amount of water can make it firmer and greatly reduce the pulling force because dry sand no longer piles up as severely in front of the runner. Water was not making the desert slippery like soap. It was changing the physics of the sand. Too little water does not help enough. Too much creates another problem. The useful method lives in the middle, which is where most ancient technology lives. Not one magical material, but the correct amount used by people who have done it before. Rollers may have helped in some settings, though rolling heavy loads is not automatically easier everywhere. Logs require suitable timber, level ground, constant repositioning, and control on slopes. A roller that escapes sideways can turn a work crew into an archaeological discovery. Sledges are stable. Ropes make force collective. Levers make small movements useful. A wooden lever placed beneath a stone does not lift the entire monument into the air. It raises one edge enough to insert a support. Then the process repeats. Lift, pack, reset, lift again. A block can rise through many small victories. This is one of the main secrets behind ancient construction, although it is not secret at all. Modern viewers imagine the final distance and ask how anyone crossed it in one action. Ancient builders divided the distance. A stone did not need to jump from ground level to the top of a wall. It could travel up a ramp, onto a platform, across prepared earth, then rise a few centimeters at a time with levers and packing. The load remained enormous. The problem became local. Stonehenge makes the principle visible because so much of the temporary technology has vanished. The large sarsen stones probably came from about 19 miles away. Smaller bluestones reached the landscape from much farther west, with sources in Wales more than 150 miles away, though the exact transport routes and methods remain debated. We do not know every step. We do know the stones were worked deliberately. Hammerstones found around Stonehenge range from larger tools for rough shaping to smaller ones for finishing surfaces. The builders carved mortise and tenon joints to connect uprights with horizontal lintels. They joined lintel ends using tongue and groove forms more familiar from woodworking. They transferred timber logic into stone. That is a profound piece of engineering. The builders did not merely stack heavy objects. They shaped connections that resisted sliding and helped the ring behave as a system. To raise an upright, people could dig a hole with a sloping approach, line part of it with wooden stakes, move the base toward the opening, then haul and tip the stone upright with ropes and a timber frame. Rubble packed around the base locked it into position. The stone appears to rise. The hole is doing part of the work. The lintels created another challenge. Timber platforms, ramps, cribbing, and levering could raise them gradually before they were fitted over the tenons. The exact arrangement is reconstructed rather than preserved, because the wood was temporary and useful enough to be removed afterward. This is why the monument creates mystery. We see the permanent stone after the construction site cleaned itself from history. Göbekli Tepe pushes monumental building even deeper into the past. In Upper Mesopotamia, communities during the 10th and 9th millennia BCE erected enclosures with carved T-shaped limestone pillars, some reaching about 5.5 meters tall. These people lived during the transition from hunter-gatherer lifeways toward early farming communities. The pillars were quarried from the surrounding limestone plateau. That location matters. A monument becomes easier when the quarry is beside the monument. Builders could outline a pillar in the bedrock, cut channels around it with stone tools, separate it, shape it, transport it over a shorter distance, and raise it into a prepared structure. None of those steps is trivial. Together they prove that monumental architecture did not wait for metal cranes, wheeled trucks, or writing. It waited for people able to organize work around a shared purpose. That purpose is harder to reconstruct than the building technique. Social events, ritual, identity, memory, competition, and cooperation may all have mattered. What the pillars clearly show is that large coordinated projects could emerge before the bureaucratic states most people assume must come first. The community did not need a modern corporation. It needed enough people to agree that this stone should stand here. The pyramids reveal the same principle at a different scale. The Great Pyramid of Giza used millions of stone blocks, many averaging more than 2 tons. Most core limestone came from the Giza Plateau itself, reducing the distance that the largest volume had to travel. Fine limestone arrived from Tura across the Nile. Granite used in important interior spaces came from much farther south at Aswan. The builders did not choose one transport method for everything. They built a network. Quarry routes moved stone to loading areas. Boats used the Nile and connected waterways. Sledges handled land transport. Ramps and work surfaces brought material upward. Teams cut, hauled, measured, placed, supplied, repaired, recorded, and coordinated. One of the oldest surviving papyrus archives includes the logbook of an official named Merer, whose crew transported limestone from Tura toward Khufu's pyramid complex. The entries are not a mystical blueprint. They are logistics. Days, journeys, crews. Stone moving through a managed system, the papyrus does not solve the exact shape of the ramps used to raise every block. That remains debated. Straight ramps, wrapping ramps, internal routes, multiple ramps, levers, and combinations have all been proposed. This uncertainty is real. It is not evidence that no practical method existed. At Hatnub, an ancient Egyptian quarry preserves a steep access ramp with flanking stairs and post holes. Researchers have suggested that ropes working around wooden posts helped crews haul stone on slopes steeper than a simple free pull would allow. That system may illuminate Egyptian hauling knowledge. It does not prove the Great Pyramid used the identical arrangement from bottom to top. Ancient construction did not need one universal pyramid. Machine. It needed several workable methods used at different stages. The lowest courses involved the greatest number of blocks but the least height. Higher courses required longer or more complex lifting, but contained less material as the pyramid narrowed. The problem changed while the building rose. A good construction system could change with it. This is where claims of impossible precision usually lose contact with the actual site. Ancient buildings can be extraordinarily accurate without every hidden surface being perfect. The Great Pyramid's overall orientation and geometry are remarkable. Individual core blocks vary. Internal fill and rough work can sit behind carefully finished exterior surfaces. Builders spent precision where precision mattered. A casing line matters. A hidden irregular gap may accept mortar and continue living privately. Modern buildings do the same thing. The visible finish receives different attention from the inside of a wall, where future residents will never stand holding a flashlight and demanding emotional closure. Ancient builders also corrected as they went. A block could be trimmed in place. A contact surface could be ground down. Small stones and mortar could fill spaces. The next course could absorb slight variation. Precision was produced through repeated adjustment, not through every block emerging from the quarry as a perfect mathematical object. And none of this happens without maintenance. Ropes fray, copper tools deform, stone edges blunt, wooden sledges crack. Workers become tired, injured, hungry, and less coordinated. Construction requires replacement tools, food production, water, shelter, medical care, storage, supervision, and people who know what should happen next when the plan fails. This is the hidden structure beneath every visible structure. A monument is a supply chain wearing stone. The person pulling the rope depends on someone twisting fiber into rope. That person depends on plants being gathered, processed, and prepared. The mason depends on quarry workers. The quarry workers depend on tool makers. Everyone depends on food, water, and a system capable of directing both towards the work site. The largest ancient machine was not the ramp, it was the organization. This does not mean every project was peaceful communal cooperation. Ancient states could demand taxes, labor obligations, and harsh work. Status and power shaped who planned, who carried, and who received the monument afterward. But the familiar image of vast structures built by random crowds whipped into moving stone is also too simple. Skilled construction needs experienced crews. A frightened person can pull a rope. They cannot automatically survey a foundation, carve a joint, manage a quarry face, or coordinate a multi-ton lift without killing everyone nearby. Expertise mattered, so did rhythm. Large groups pulling together must apply force together. Work songs, calls, visual signals, and supervisors can synchronize effort. 20 people pulling at slightly different moments waste energy. 20 people leaning into the rope on one signal briefly behave like one larger body. That body can be enormous. Ancient builders extended human strength by connecting people through materials. Rope connected hands, language connected timing, measurement connected separate parts. Memory connected one generation of builders to the next. This is why asking how ancient humans built without modern tools slightly misses the point. They had modern tools, modern for them. They had tools adapted to their resources, structures adapted to their tools, and societies adapted to projects that lasted longer than one person's attention span. They did not defeat physics, they understood enough of it to stop wasting force. They reduced friction, used gravity, changed angles, spread loads, repeated small movements, placed the quarry near the site when possible, moved heavy material by water when water was easier than land, made weak materials strong through shape, made human bodies stronger through coordination. The impressive part is not that they built like us without our machines. They built differently because our machines did not exist. And when the building was finished, the ropes were reused, the ramps disappeared, the timber frames decayed, and the instructions remained inside people who eventually died. Only the stones stayed. That is why the monument looks impossible. The tools are gone. The intelligence is still standing.